just real quick, let me, for the video's sake, I know I already told y'all this, but let me just show, for those students that aren't here today, the big picture for the day is to take this, or really any graph, and rotate it about the x-axis or the y-axis to form a solid. And I have drawn this function here, which is the border of this shape, and if we rotate it about the x-axis 360 degrees, now this is not perfect obviously because of the shape down here at the end, but this just gives you an idea that we're finding the volume of a 3D image that's been rotated about either the x or the y-axis. So that's the big picture. And these are the notes for 6.2, not 6.1. And it's called Volumes of Solids of Revolution. And we're talking about two different methods, the disk method and the washer method. So if you'll look at the guided notes with me, what you see here is a parabola, or half of a parabola in the first quadrant. It says that we have the region in quadrant 1 bounded by the parabola y equals 4 minus x squared. Hopefully you recognize that because it's a parabola that's been reflected over the x-axis and shifted up 4 units. And we're looking at only the area bound in the first quadrant. And they're saying that this time we're going to rotate it about the y-axis to form a solid as shown above. So if we take this parabola in the first quadrant, if we take that area and we rotate it this time around the y-axis, 360 degrees, can you see the solid that is formed by rotating it about the y-axis? What we're going to do is we're going to find the volume of that 3D solid. That's what our goal is. So to do that, we're going to do something called the disk method. So my first question is, does anybody know how to find the volume of a disk? Volume of like volume of a cylinder. Volume of a cylinder. Like if you think about this disc here, I'm trying to find the volume of it.
Area of the circle times the height.
Area of a circle times height. What's the formula for area of a circle? Pi r squared. So the volume is going to be pi r squared h. Okay, if I want to find the area of just this disc here. That's from geometry. If you've forgotten, it's no big deal. But I'm just reminding you that to find the volume of a cylinder, which is the shape of this disc here, to find the volume of a cylinder, you're going to do pi r squared h. So let's actually write that down over here to the side. Volume equals pi r squared times the height, which we're calling h. Okay, now if you look under number 1, it says a representative slice of the region is shown in the figure at the left. As the slice turns, it generates a plane disk as shown in the figure at the right. So we're just taking a slice of this area, and we're going to take that slice and we're going to rotate it about the y-axis. And when you rotate it about the y-axis, it forms this disc that you see here in the 3D picture. And so it says find the volume, which we're calling dV, find the volume of the slice in terms of the coordinates of the sample point. The sample point is xy. Don't forget that the equation is y equals 4 minus x squared for this particular function. So what we're going to do is we're going to use this formula, v equals pi r squared h, and we're going to write a specific formula for this little disc that we have, they have created for us. So we're going to call the volume of that one little disc dV, and we're going to use pi r squared h Pi is just a number. Now, for R, I want you to leave R for a minute. So pi R squared, and I want you to leave H for a minute. Leave it blank. Because I want to talk about what they are for this specific problem. Well, for this specific problem, what value represents the radius of this disk? X, good. The radius is represented by X. Does everybody see that? The X value or X coordinate tells you the length of the radius of that disk. So that's what I'm going to put in for R. And then the height of the disk, they're telling us here, we're going to call is dy is the height of the disk. Change in y value is the height of the disk, dy. So our expression for the volume of just one disk is dV equals pi x squared dy. What we're doing here is we're discovering the formula for finding the volume of any solid, okay? I'm just trying to show you where it's coming from, okay? So let's keep going. By appropriate algebra, transform dV so that it is in terms of y alone. So I have dV equals pi, and I need to sub in something for x squared. I need to get it only in terms of y. So if you look back up at the function, y equals 4 minus x squared, and we solve it for x in terms of y, you'll see that x squared is equal to what? What's x squared equal to? 4 minus y. Because you move the negative x squared to the left, it becomes positive x squared. Move the y to the right, it becomes a negative y. 4 stays positive. So x squared equals 4 minus y. So we're just going to make that substitution, 4 minus y, in the place of x squared. Now we're not going to square it because it's equal to x squared. Okay? So it's going to be 4 minus y dy. And then for part 3, or number 3, it says find exactly the volume V of the solid by adding the volumes of the slabs and taking the limit as the thickness of the slabs go to 0. Okay, so let's think about that for a minute. In this class, how do we represent adding stuff together? The summation symbol, right? If we use the summation symbol, we're adding stuff together. So if you add up, if we apply the summation to both sides, and then take the limit, on the left-hand side, you're adding up all the dVs. So what they're saying is, okay, we're not just finding the volume of one disk. We're going to pick another piece up here, and we're going to rotate that around the y-axis, and we're going to find the volume of that disk, and then we're going to pick another piece down here. We're going to rotate that around the y-axis. We're going to find the volume of that piece. In fact, we're going to stack up infinite number of disks. So take the limit as n approaches infinity. And what will that actually give us if we add all those little volumes together? It will give us the actual volume of the solid, right? If we add the volume of each of the little disks, that's going to give us the actual volume. So the sum of all the dVs, we're just going to call V. And then when you take the limit of the summation dy here, what that's doing, that's just the definition of integral. When you take the limit of the summation, and so we're going to take the integral. In this case, we're gonna go from 0 to 4. You may tell me where I got those bounds? Where did I get 0 to 4? It's how high it is. Because I'm integrating dy, I have to use y values. Okay? So integrating from 0 to 4, if we were integrating dx, I would have used 0 to 2, the x values. But I'm integrating dy, so I use the y values, pi times 4 minus y dy. And then I can actually pull my pi out, integrate from 0 to 4, 4 minus y dy. And that will give me the volume of that solid. Okay, let's go ahead and do it. That's pretty easy, isn't it? Why could I pull that pi out? It's just a constant, it's just a number. And so I'm going to pull the pi out. I usually use some brackets here. And then multiply it into my final answer. What's the antiderivative of 4 with respect to y? 4y. Antiderivative of y with respect to y? Y squared over 2, or 1/2 y squared, from 0 to 4. So we have pi times, let's see, 16 minus 8 minus 0. And that's going to give me what for my volume? 8 pi, good. So 8 pi is the answer I'm looking for. So as I mentioned in the beginning, sometimes we're going to be rotating about the x-axis, sometimes we're going to be rotating about the y-axis. So here's just a couple of things to remember. If you're rotating about the y-axis, as we just did, you're going to be integrating dy, and you have to write your equation in terms of y. And your bounds have to be y values. If you're going around the x-axis, you're going to be integrating dx. Your equation is going to be in terms of x, and your bounds are going to be x values. So those are some things that you need to remember. But the big idea is to find the volume of a solid. You're going to technically do integration of pi r squared h, where h is just your dx or your dy. Pi is a constant, so you can pull it to the outside, so that will always be in your formula. Pi will always be in your formula. And then your radius is going to be squared in most cases. In this case it wasn't, because it was x squared and we had x squared in the formula. Okay, so we're integrating pi r squared h. That's our formula for finding the volume of a solid. That's what we've just sort of developed. Okay? Now, if you will flip over to the back, we're going to talk about the washer method. So if you look at 5-9b, you'll notice on this example we have two equations. So here is my first equation, here is my second equation, and what we're looking at is the area between those two curves. And we're going to take the area between those two curves, so see this area here? You're going to take that area, and this time we're rotating around the x-axis. Can you visualize the 3D solid that will form when you rotate that around the x-axis? Well, you can see at the bottom they have given you a diagram of that shape, the 3D shape. So in this case, can you see how there's a hole in the middle? Yeah, it's a parabolic shape, isn't it? So if there is a hole or you have concavity, then you're gonna have to use the washer method. So on the other one, it was a solid. There was no hole, it was just a solid paraboloid. We've used the disc method on those. If it has a hole in it, you gotta use the washer method, okay? And that's what we're gonna talk about next. Did you have a question?
No.
Okay. All right, so we're taking this piece, we're rotating it around the x-axis this time, and it says the figure above shows the region R that is bounded above and below by the graphs of y sub 1 and y sub 2. Can you identify if the top graph is y sub 1 or y sub 2? Y sub 1. Everyone hopefully should recognize that y sub 2 is the parent graph for square root of x. Y sub 1 is an exponential decay function. May not be able to pick that out as easily as the square root function, but I think looking at the two functions, you can certainly identify that the top function is your y sub 1, the bottom function is y sub 2, just knowing the parent graph for square root of x. It says on the left and the right by the lines, it's bounded by, on the left and the right by the lines x equals 1 and x equals 4. And the figure below shows the solid generated by rotating R about the x-axis. A strip of width dx generates the plane washer of thickness dx whose cross-section is a circular ring of outer radius y sub 1, inner radius y sub 2. Now, one thing that we're going to have to think about when we find the volume of this solid is we're going to take the hole radius, W-H-O-L-E, and we're going to subtract off the hole, which is H-O-L-E. So you're going to take the solid, the whole volume even, as if it were solid, but then you're going to subtract off the volume of the hole that is cut out. And so we normally say the whole minus the whole equals W, which is what you want. The whole minus the whole equals what you want. So you're going to think about the radius as if it didn't have a hole in it. What would it look like without the hole? You're going to come up with an expression for that, and then you're going to subtract off the expression which represents the H-O-L-E hole. All right, so number 1 says write the area of the circular ring as a function of y sub 1 and y sub 2, and then use the result to write the volume of the washer. So we're still doing pi r squared h. Okay, but we're just going to subtract off the volume of the hole as well. So we're going to call this dV.
Scroll up.
Yes, sorry. And so what would represent the, I sometimes call it the entire, W-H-O-L-E, I'll say the entire radius, just to distinguish so I don't have to keep spelling hole and hole over and over again. So what would be representative of the entire radius? If you look at this figure over here and we just take out one piece, yeah, it is going to be y sub 1, good. So if you think about cutting a slice, that's going to be representative of the entire radius if it were a solid, like a true solid without a hole in it. Then that would be representative of the y sub 1. So I'm going to say pi times y sub 1. Oops, I did a superscript instead of a subscript. pi times y sub 1 what? Squared, because it's pi r squared, right? Times h. What would the height be in this case? This time it's dx, isn't it? Because we're going around the x-axis. And then I'm going to subtract off pi times the radius of the hole, which is going to be y sub 2. The radius of the hole would be this radius here. I can pick it anywhere, by the way. But if I pick one slice of it, the slice is going to be here, and that's going to be representative of y sub 2. Does everybody see that? The radius of the HOLE hole is just going to be y sub 2. Because if I pick it over here, it's going to be smaller than if I pick it over here. But it doesn't matter as long as I use my y sub 2, which is on the square root of x. So I'm going to say y sub 2 squared, and that's still dx, because we're still going around the x-axis. Now for part 2, it says transform that equation for dv so that it is in terms of x alone. Well, that's actually pretty easy in this case, because all we have to do is sub in our equations for y sub 1 and y sub 2. And so dv equals pi times, what is the y sub 1 equation again? 6e to the negative 0.2x dx minus pi times y sub 2 is just square root of x, and then we're going to square it.
Yeah, that's where the other.
Oh, yes, I'm sorry. dx. We have to square both of them. Pi r squared dx. And so now they want us to add up all the dv values. This is just for one little disk. We want to add all the disks up and take the limit as the number of disks approach infinity. And so that means, let's actually clean it up a little bit before we do the transformation. Let's say, is everybody okay if I write it like this? Pi times 6e to the negative 2x quantity squared minus x dx. So what I did is I factored out a pi and a dx, but I put the pi at the beginning and the dx at the end. Because both terms, these are two terms, both terms had a pi and a dx in it. So I factored the pi and the dx out, but I put the pi at the beginning and the dx at the end. Why would I do that?
So it's
Right,
like,
when you're done with,
Yeah, because I'm getting ready to take the integral of it, right? I'm getting ready to rewrite it as an integral. And so we want the dx at the end, pi is a constant, we want to move it out of our way, put it at the beginning. And so if we do just like we did on the front side, we take the summation of both sides. Summation of all the volumes gives you the actual volume of the solid. If you take the limit as n approaches infinity of the summation of this expression, it gives you the integral. What would be our bounds on this integral? Does it say 1 to 4? Oh yeah, it is bound by x equal 1 to x equal 4, you're right. It looks like 0 on this one because of the hole, but if you go back and read the definition of the function, it says it's bound on the left and the right by x equals 1 and x equals 4. The important part also is knowing that you're using x values this time because we're integrating dx. So it is 1 to 4. Let's go ahead and write this as 36 e to the negative 4x minus x.
It was 0.2.
What's 0.2?
It's the exponent.
Oh, gotcha. This one here?
Yeah.
Thank you. So when we square it, you're just multiplying the exponents, and I'm gonna pull my pi out to the front to get it out of my way, and then dx. And then we can use a calculator if we want to integrate from there. For sake of time though, I'm gonna move on and let you guys do that for tonight, okay? Just get me an answer for that using your calculator. All right, flip over to the next page. Look at number 1. Number 1 says the region under the graph y equals square root of x from x equals 0 to 2 is rotated about the x-axis to form a solid. Find its volume. So now we don't have to go through all of these steps for each of these problems. The purpose of this sheet is to show you where the formula comes from, okay? Now, all you have to really remember is that we're integrating pi r squared h, where h is dx if we rotate around the x-axis, it's dy if we go around the y-axis, okay? So, this time we're rotating about the x-axis. By the way, am I going to use the disk method or the washer method on number 1? That's going to be disk because it doesn't have a hole in it. It's truly solid 3D. So, to find my volume, and we're just going to set each of these up and I'll let you go back and work them on your own, okay? But the volume is going to be, always start with pi, times the integral from what to what? 0 to 2. Because we're integrating with respect to x or y? With respect to x, because it says around the x-axis. So I'm going to put my dx over here. That's my height. What's the only thing I'm missing from my formula? My r squared, the radius squared, because I'm integrating pi r squared h. Here's my pi, here's my h, I just need my r squared in the middle. So the r squared is dependent upon the radius, and just take a slice. It says we're rotating about the x-axis, so make sure your slice is perpendicular to the x-axis. And think about what value would give you that radius. It's going to be y. You see how the y value would give you the radius depending where you are? Where you pick your slice, I guess. Because I can pick my slice down here. The radius is going to be the y value of that slice. If I pick it here, it's still going to be the y value. It's going to be a bigger y value. If I pick it over here, it's going to be a bigger y value. But no matter where I pick the slice, it's going to be a y value. So I'm going to say y squared. But I can't stop there. What's wrong with that?
Because you don't say in terms of x.
Yeah, I need it in terms of x because I'm integrating dx.
Y.
So we use our formula y equals square root of x, and we solve it, or we don't have to solve it, it's already solved, but we sub in what?
Square root of x.
Square root of x. And when you square the square root of x, you get plain old x. So here is my formula, and I'm going to let you guys go back and do that a little bit later for sake of time. All right, let's look at number 2. Number 2 says the region in the first quadrant bounded by the parabola y equals 1 minus x squared is rotated about the y-axis to form a solid. Find its volume. First thing you want to figure out is it a disk problem or a washer problem? This one's still a disk problem, right? So we don't have to worry about subtracting off the HOLE hole. What's the difference in number 2?
It's around y.
This time we're going around the y-axis, so that means we have to integrate dy. So I'm gonna set up volume equals the integral dy. And let's go ahead and put our pi out front so we don't forget it. What about our bounds?
Oh, it's the first one.
It's only the first quadrant, that's right. The solid is, or the area that we're rotating is in the first,
So it's gonna be 0 to 1.
so it's gonna be 0 to 1. Does everybody see that? Even though it's not labeled 1, the parabola is the equation y equals 1 minus x squared, which means it's flipped over the x-axis and shifted up 1 unit. And we're using y values for our bounds this time because we're integrating dy. Okay, so we go 0 to 1. And we need our radius, which this time if we pick a slice, it's going to be perpendicular to the y-axis, and that length is represented by the x-coordinate. So we're going to say x and square it. And so what is x squared equal to in this case? 1 minus y. Good. And it doesn't need to be squared because x squared equals 1 minus y. And then I'll let you go back and work that one out to get a value. Okay, let's look at number 3. The region bounded by y equals 2 minus x squared and y equals 1 is rotated about y equals 1. Find the volume of the resulting solid. Scary? No, it's not that scary. But the difference is we're not rotating about the x or y axis this time, but we're rotating about a horizontal line, which is not a big deal because it's the same as if we were rotating about the x-axis. It's acting like the x-axis.
We'll just change our.
So, are we integrating dx or dy? Dx, because that line is acting like the x-axis. The orientation in which I'm rotating is acting like the x-axis. Is it a disk or a washer method? It's still a disk method. What if I rotated about the x-axis? Then it's going to be washer method. Do you see the difference? There would be a hole in it if you rotated about the x-axis, but since we're rotating about y equals 1, we're in good shape. All right, so let's set it up. Volume equals pi times the integral, and we said it is dx. And it's still the disk method. Let's talk about our bounds. Do we use x values or y values? We use x values because we're integrating dx. So it's going to be from here to here. So 0 to 1. 0 to 1. If you put 1 in for x, you get 1. So 0 to 1. And if I take a slice, 1 disk, now think about this one for a minute. How would I find the radius of 1 disk? Whether I pick the disk here, or over here, or over here. What is it? Y minus 1. Yeah, y minus 1. Because we have to subtract off the 1, even though we're not rotating it around the x-axis, we're still trying to figure out what this y value is. And then we've got to subtract off the 1 for this area here. Because the y value would give you this entire length. Okay, so we say y minus 1. And then we need to, what about square it? Gotta square it. And so now we've got to change our y in terms of x. So what's it gonna look like? So let me write it as 2 minus x squared minus 1 so I don't lose anybody. But then of course you can certainly combine the 2 and the 1 and make it integral from 0 to 1 of 1 minus x squared squared dx. Okay, questions on the first page? All right, let's look at number 4. Find the volume of the solid formed by revolving the region bounded by the graphs of f of x equals square root of x and g of x equals 0.5x about the x-axis. There's going to be a hole this time, right? So this time we have to use the washer method. We have to use the washer method. So we're going to still do volume equals pi times the integral. We're rotating it about which axis? X-axis, so that means we're integrating dx. So we're going to do whole minus whole. Entire radius minus the radius of the whole. So which value would be representative of the entire radius?
The what?
So let's call this y sub 1. And then we'll call the radius of the whole y sub 2. So we're going to do y sub 1 squared minus y sub 2 squared. Now notice the difference in 3 and 4. In 3 we just have one radius, but we had to subtract the 1. That's why it was only squared once. But in this case we've got to take the entire radius squared minus the radius of the whole squared. Just like we did back here in our notes when we were developing the formula. Notice how we squared the radius of the first minus squaring the radius of the second. So you have to square the radii individually. And now what about my bounds? Looks like it's hard to see, isn't it?
0 to 2 is
I think it's actually 4, isn't it? The numbers are really, really